Hello students, welcome to the fourth lecture on the lecture series on probability. So previously we were doing some exercise problems. Before that we did some theory problems, right? And before that we discussed all the type of basic concepts and types of problems that are usually involved in this topic, probability. So let's start this topic and do some exercise problems. So we'll be covering exercise problems, right? So let's start with problem number 1. Okay, so there are actually 3 boys and 3 girls and they sit in a row at random. So what is the probability that all the girls can sit together? Okay, so basically there is b1, b2, b3. Okay, these 3 denote the 3 boys and 3 girls are denoted as g1, g2 and g3. Okay, so basically there are 6 distinct members, right? But in terms of characteristics, that is whether they are boy or girls, okay, so they are different. Okay, so the probability that all the girls sit together, so let's see the sample space first. So in how many way these can be arranged? So these can be arranged in what? 6 factorial ways. That is equal to, here for the first place it will be what? In a row, if we make a row for 6 people, it will be something like that. So here one will sit, 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 and here one will sit, right? So 6 factorial will be what? How? Because for this one there are 6 choices, right? Because one has sit right here. So for this one the remaining choices are 5. For this one the remaining choices will be 4 because 2 have been already seated. So for this one there will be 3 more choices, and for this one there will be 2 more choices, and for this there will be only one choice left. Okay, so basically if we accumulate these all and multiply it by together, what will happen is we'll be getting 6 factorial right there, right? So basically the sample space cardinality is what? 6 factorial. So let's try to see the event. So event is what? That all the girls, so event is all the girls sit together, right? So this is the event. So it will be what? So we can actually assume, for this we need to do something else. We need to do what? We need to assume that these people as 1. Okay, let they be denoted as z. So basically we have b1, b2, b3 and b4 and g. Okay, so in how many ways these can be arranged? So these can be actually arranged in 4 factorial, because for this place you will have 4, for this you will have 3, for this you will have 2, and for this you will have one choice. So multiplying these, what will be left with you is 4 factorial, right? So since you have 4 factorial right there, so what will happen is inside that the 3 girls can be arranged in how many ways? So basically you have 3 girls, so g1, g2 and g3. So in how many ways these 3 can be arranged? For the first place there are 3 options, for the second there are 2, for the third there are 1 option. So they can be arranged in 3 factorial ways. Okay, so first you have to consider this case, then you have to multiply with this case, because inside that g they can be arranged in 3 factorial ways. So e will be cardinality of, so this implies that cardinality of e will be equal to 4 factorial into 3 factorial. Okay, so how we can actually calculate the probability of e? So probability of e is equal to what? Cardinality of e by cardinality of the sample space. Okay, this is the general formula for any probability, or for any probability of event, right? So it will be equal to what? 4 factorial into 3 factorial by 6 factorial, right? So it will be equal to what? So it will be 3 factorial by 6 into 5 factorial, right? So this will be 3 into 2 by 6. Sorry, 3 into 2 by 6 into 5. So it will be equal to what? So this will actually be equal to 1 by 5. So the probability will be 1 by 5. Okay, that all the girls sit together. So basically the problem asked us that if 6 boys and 6 girls sit in a row at random, the probability that all the girls sit together will be what? So we want, so how it can be calculated? It can be calculated by first assuming that all the 3 girls are 1 girl. Okay, then doing their what? Permutations. Then we are left with what? But the answer will be 4 factorial ways, right? And how we can actually permute 3 girls? Okay, so they can be permuted in 3 ways, 3 factorial ways. So multiplying these two, we can actually get how all the girls can sit together, or we can actually find out the cardinality if all the girls sit together. Okay, so their cardinality will be nothing but what? 4 factorial into 3 factorial. Then we divide it by what? 6 factorial to find out the probability of that event. Okay, so what we are left with is 1 by 5. So 1 by 5 will be the correct answer. So let's go forward to the next question. Let's see what problem number 2 tells us. So if A and B are two candidates, okay, seeking admission in an engineering college, okay, so the probability that A is selected is what? 0.5, and the probability that both A and B are selected is at most 0.3. Then is it possible that the probability of B getting selected is 0.7? So let's try to figure out what the question is telling us. Then we'll try to figure out what it is actually asking us. Okay, so given that we are having what? A and B as two candidates. Okay, what they do? They seek admission to an engineering college. So basically we have A and B, and they seek to take admission in an engineering college. Probability that A is selected. So this implies that probability of A is equal to 0.5. Okay, and probability that both A and B are selected is at most 0.3. So probability of A intersection B is less than equal to 0.3, because it is told to us that probability that both A and B are selected is at most 0.3. So is it possible that the probability of B of getting selected is 0.7? Okay, so can it happen? Okay, let's try to figure out. So let F1 be the event that A is selected in the engineering college, and F2 be the event that B is selected in the same engineering college, right? So then we have that P of F1 is equal to 0.5 and P of F2 is equal to 0.7. So let's say it is 2, right? That is probability of B is 0.7. So given that probability of F1 intersection F2 is less than equal to 0.3, right? So now probability of F1 into probability of F2 is less than equal to 0.7. Okay, why you will say that we are writing this? From this, how we can actually conclude this? Because probability of A getting selected, right? Getting A selected doesn't affect getting B selected, right? So we can say that these two are actually mutually independent events. Mutually independent events, right? So we can actually write that probability of if A and B are mutually independent, then probability of A intersection B is equal to probability of A into probability of B, right? So we can write it as what? Probability of F1 into probability of F2 is less than equal to 0.3. So what will happen is, so we are given that probability of F1, right? So this implies that probability of F2 will be what? Probability of F2 must be less than equal to 0.7. But probability of F2 is given as what? It is asking us, can it happen as probability of B is actually equal to what? 0.7? Actually no, because it must be less than equal to 0.6. So that is why the given statement is false, using the theorem of mutually independent events, that if two events are mutually independent, then the intersection of those two events, or the probability of the intersection of those two events, is actually equal to multiplication of individual probability of the two events. Okay, so that is what we are written here. Okay, so let's go forward to the next question, that is problem number 3. So the probability of an occurrence of event A is 0.7 and that of occurrence of event B is 0.3, and the probability of occurrence of both is what? 0.4. So probability of A is equal to 0.7, probability of B is equal to 0.3. Okay, so probability of occurrence of both is what? 0.4. So probability of A intersection B is actually 0.4. Okay, so this is what given to us, right? So we know that probability of E intersection F will be what? Probability of E into probability of F, because these two are independent events. So probability of E intersection F will be 0.21. So given that probability of E intersection F is what? 0.4. So the given statement is actually false. Okay, so if the probability of occurrence of event A is this, occurrence of B is this, then the probability of both is this is actually false. When actually those two, A and B, are mutually independent. Okay, this is the statement that is actually missing out from the question. So if this is the condition, then this is never possible. Okay, so let's go forward with problem number 4. So 10 card numbers 1 to 10 are placed in a box and mixed up thoroughly, and then one card is drawn randomly. So if it is known that the number on the drawn card is more than 3, what is the probability that it is an even number? Okay, so there are 10 cards from 1 to 10 placed on a box, mixed up thoroughly. Then one of the card is drawn at randomly, and it is known that the number on that drawn card is more than 3. Okay, what is the probability that it is an even number? So it is known that the number that is drawn is what? More than 3. So how many numbers are that are more than 3 and less than equal to 10? So 4, 5, 6, 7, 8, 9, 10, right? So this is our sample space right now. So how many among these are actually even? This is even, this is even, this is even, this is even. So there are basically 4. So probability of E will be equal to, cardinality of E will be equal to 4. So cardinality of sample space will be what? 1, 2, 3, 4, 5, 6, 7. So it will be 7. So probability of E will be what? Probability of E is equal to cardinality of E, that is equal to 4, by cardinality of S, that is equal to 7. So this will be the probability of the event. Okay. So let's go forward and see problem number 5. So as you can see here, probability of A given that B has happened is equal to what? We can also use this formula. Okay, so let's see the solution so that we can also solve it in a different way. So let A be that event that the number on the card is drawn is even. Okay, and B be the event that the number on the card drawn is greater than 3. So we have to find that probability of A given that B has already happened. Okay, so now the sample space of the experiment S will be equal to what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this will be the sample space. So then A is equal to what? 2, 4, 6, 8, 10. And B is equal to what? 4, 5, 6, 7, 8, 9, 10. And A intersection B will be 4, 6, 8, 10. Right? So probability of A will be what? 5 by 10. Probability of B is equal to what? 7 by 10. Probability of A intersection B will be what? 4 by 10. So probability of A given that B has happened is equal to probability of A intersection B by probability of B. But given that probability of B is equal to what? 7 by 10. So probability of A intersection B is given also that 4 by 10. So what will happen? We can cancel out 10 and what we are left with is 4 by 7. So let's go forward with problem number 5. So in a school, there are 1000 students, out of which 430 are girls. Okay. So among the 1000 students, 430 are girls. So the remaining ones are what? Boys, right? So how many boys are there? So 570 boys are there. 570 because 1000 minus 430 is equal to what? 570, right? So it is known that out of 430, 10% of the girls study in that class. What is the probability that a student chosen randomly studies in class 12 given that the chosen student is a girl? Okay, let E denote the event that a student chosen randomly studies in class 12, and F be the event that the randomly chosen student is a girl. Okay, so we have to find probability of E given that F has already happened. So probability of F will be equal to what? 430 by 1000, that is equal to 0.43. Probability of E intersection F will be 0.43 by 1000, that is equal to 0.043. So given that probability of E such that F has already happened is equal to what? Probability of E intersection F whole by probability of F. So this implies that this will be equal to what? 0.043 by 0.43, it will be 0.1. Okay. So an urn contains 10 black and 5 white balls. Okay, so number of total balls will be what? 15, right? So 2 balls are drawn from the urn, one after the other, without replacement. Okay, so what is the probability that both drawn balls are black? Okay, so basically we have a urn, right? So we have a urn right here. Okay, so basically you have a urn and there are different balls, right? Red ball and white and black balls. Okay, so we have other balls too. So 2 balls are drawn from the one after the other without replacement. So without replacement is a word that you should keep in your mind, because this is the keyword right here. Okay, so after drawing one ball, how many balls are there? 14 balls are there right now. So it is telling us that what is the probability that both the drawn balls are black. Okay, so the first probability that the first ball drawn is black will be what? So 10 by 15, right? Because there are total 15 balls, and the possibility that it will be a black is what? 10, because there are 10 black balls. So then we multiply with what? 9 by 14, because there are now 14 balls are remaining, since one is already black. So how many black balls are there? 9. So this will be equal to 15 into 14, 9 into 10. Okay, simplifying further, it will be 3 by 5 into 5 into 2 into 7 into 2. So cancelling 2 out, what we are left with is 15 by 35. So 15 by 35 will be the answer. So simplifying further, what we can say, this is 3 by 7 actually. So let's see the step-by-step solution. So let E and F denote the respectively the events that first and second ball drawn are black. So we have to find probability of E intersection F or probability of EF. Right, so probability of E is equal to P, that is equal to 10 by 15, and probability of F will be what? It will be 9 by 14, because the probability that the second ball drawn is black, given that the ball is first drawn ball is actually black, is nothing but the conditional probability of F, given that E has occurred. So it will be 10 by 15 into 9 by 14. So the answer will be 3 by 7. Let's try to see problem number 7. So a die is actually thrown, and E is the event that the number appearing is a multiple of 3. So F be the event that the number appearing is even. Then find whether E and F are independent, right? So we want to know whether E and F are independent, and what is given to us? That is, a die is actually thrown, and E is the event that the number appearing is a multiple of 3. So in a die, what are the possibilities? 1, 2, 3, 4, 5 and 6, right? So what is the sample space that the given number is, or the appeared number is actually a multiple of 3? It will be 3 or 6, right? And nothing else is actually a multiple of 3. So probability of E will be what? 2 by 6. That will be equal to 1 by 3 by further simplification. F be the event that the number appearing is even. So E dash, let that. So F is the new one, right? So F will be what? So F is equal to 2, 4, 6, right? So probability of F will be equal to what? It will be 3 by 6, that is equal to 1 by 2, right? So find whether E and F are independent. Okay, so can actually happening of one affect other? Yes, they are not independent. Okay, because probability of E intersection F, okay, that is, it is also even, and they are what, and it is an even number and a multiple of 3. What will happen is this will be equal to 1 by actually 6, right? But probability of E into probability of F, that is equal to 1 by 3 into 1 by 2. Okay, so this is equal to 1 by 6. So since actually this implies this implies this, so we can say that if probability of E into probability of F is equal to probability of intersection F, we can say that E is actually independent of F. Okay, so the answer will be yes. So we know that the sample space is what? 1, 2, 3, 4, 5, 6, because if you throw a die, there are only 6 options. Either 1 will be there, 2 will be there, 3 or 4 or 5 or 6. So E is what? Multiple of 6, right? So multiple of 3, right? So it will be 3 or 6. So F is what? Even number. So 2, 4 or 6. So E intersection F will be what? 6, right? So probability of E is equal to 2 by 6 is equal to 1 by 3. So probability of F will be 3 by 6 is equal to 1 by 2. So probability of E intersection F will be 1 by 6. So clearly that probability of E intersection F is equal to probability of E into probability of F. So hence E and F are independent events. Okay. So E and F here given are independent events. Okay. So let's see problem number 8. So a bag contains 9 discs, of which 4 are red, 3 are blue, 2 are yellow. The discs are smaller in, similar in shape and size. So a disk is drawn at random from the back, and what we need to do is we need to calculate the probability that it will be actually red, yellow, blue, not blue, either red or blue. Okay, so let's see. So there are actually 9 disks, right? So in all, so that the total number of possible outcome will be what? 9. So the events A, B, C can be defined as what? The disk is drawn is red. For A, it will be what? The disk drawn is red in color, and the disk drawn is yellow will be what? Represented by B, and the disk drawn is blue is represented by C. Okay. So the number of red disk is equal to what? 4. So Na is equal to 4. So probability of A is equal to 9 by 4. It will be actually 4 by 9. Okay. So it will be equal to 4 by 9. Number of yellow disk is equal to 2. So it will be actually what? 2 by 9. Probability of B is equal to 2 by 9. So the number of blue disk is equal to what? 3. So it will be actually 1 by 3. So probability of C is equal to 1 by 3. Clearly, the event not blue is not C, right? So probability of C complement is equal to what? 1 minus probability of C. It will be equal to 2 by 3, because 1 minus 1 by 3 is equal to 2 by 3. So the event that either blue or red, okay, may be described as what? A or C. So probability of A union C is equal to probability of A plus probability of C minus probability of A intersection C. But these are two mutually independent events. Okay, so they cannot actually happen together. So it will be equal to what? 4 by 9 plus 1 by 3. That will be equal to 7 by 9. So on her probability 9, problem number 9. So on her vacations, Veena visits 4 cities. So what does Veena do? She visits 4 cities, A, B, C and D. Okay. So in random order, okay, there is no order given to us. So what is the probability that she visits A before B, and A before B, and B before C? So the number of arrangements or orders in which Veena can actually visit the 4 cities is 4 factorial way, because for the first city it can be any one of the 4, and for the second it will be any one of the 3, because she has already visited one place, right? And similarly we can say that it will be 4 into 3 into 2 into 1, that is equal to 4 factorial or 24. So therefore NS, that is the cardinality of the sample space, will be equal to 24. So since the number of elements in the sample space of the experiment is what? 24. All these outcomes are considered to be equally likely. So a sample space for the experiment is S is equal to ABCD, ABDC, ABCD and what? DCBA. Okay. So you can see all of these. Okay. But we don't really need to see it. So let the event that C visits A before B. So among these you can see in which case actually A comes before B. Okay, here it comes, here it comes, here it comes, here it comes, here it comes. Okay, you can see in all these cases. So probability of E will be what? Cardinality of E by cardinality of the sample space. It will be 12 by 24. So it will be 1 by 2. So let's see the second case. That is the event that Veena visits A before B and B before C. So how many cases are there? ABCD, or it will be DABC, or ABDC, or ADBC. Only among these 4, only one order is possible, right? So probability of F will be what? Cardinality of F by cardinality of the sample space. So 4 by 24. So this will be actually cumulatively equal to 1 by 6. Let's see problem number 10. So find the probability that when a hand of 7 cards is drawn from a well shuffle deck, 52 cards, it contains all kings, 3 kings, at least 3 kings. So the number of total possible hands is what? 52C7. So the number of hands with 4 kings will be 4C4, because there are only actually 4 kings, and 48C3. So other 3 cards must be chosen from the rest 48 cards, right? Because there has to be chosen 7 cards. So hence P is equal to a hand will have 4 cards will be equal to what? Probability of that event, sorry, cardinality of that event by cardinality of the whole event. So it will be actually 1 by 7735. So I believe that's enough for today. Thank you.